so welcome back. Our next speaker is Rand Tesler from Weizmann. He's going to tell us about a magic number property for the m equals to 2 amplitude.
Thank you. So everyone hears me?
Yes.
Okay, cool. So I'm going to talk about the magic number property for the m equal to amplitude. It's based on a joint work with Matteo, Melissa, and Lauren. So I will start by talking a little bit about amplitude tiling and the magic number conjecture. So, I mean, I tried to see some of the talks, but I wasn't able to see all of them. So I don't know if amplitude tilings were already mentioned, but I do know that amplitude was defined. So I will be relatively brief. So the amplitude was defined by Nima and Yara 11 years ago in the following way. So let k, m, and n be three natural numbers, where n is at least k plus m. And let V be a positive n times k plus m matrix, meaning that all its maximal minors are positive. So the true amplitude is the image of the amplitude map, which takes the non-negative Grassmannian into the Grassmannian kk plus m by right multiplication. And okay, so this geometric space was defined as part of the study of Arkani, Hamed, and Trenka of the n equal 4 super-Yang Mills theory. And somehow, well, the justification to study it from the physics point of view was the existence of certain tilings of this space, which is, well, rather complicated, into simpler pieces. So from the physics side, it was known that one way to calculate scattering amplitudes of planar n equal 4 theory was using the BCFW recursion. And those tilings that were somehow predicted in the same moment that the amplitude was defined were a geometric manifestation of this recursion. Okay, so let me say what do I mean by a tiling. So I will follow the definition of Bauer and He. There could be stronger definitions, but I mean, for physics needs, we don't need them, even though for well, mathematically, we can find tilings which actually satisfy much stronger requirements. So the three requirements are, first of all, that each positroid cell in the collection. Okay, so a tiling is a collection of positroid cells, and we require each positroid cell to map injectively into the amplitude. We want the images of cells to be disjoint, images of different cells, and we want the closures of images to cover the whole amplitude, the union of closures. Okay, so as I said, for m equal 4, the first tilings that were found were generated from the BCFW recursions. Very recently, in a work with Chaim Tzvika, Matteo, Melissa, and Lauren, we found new types of tilings that even involve cells which are not BCFW, but originally these were the original tilings that were found. Then for m equal 2, Bauer and He discovered another recursion, which is like an m equal 2 BCFW, and they showed that the corresponding cells cover tile the amplitude. And triangulations of the k equal 1 amplitude, which is the cyclic polytope that I'm going to talk about in the next slides, is actually their study a much older topic, and so they were studied by many authors, especially by Rambau. Okay, so let's take a look at the cardinalities of tilings. So it is easy to see that when k equals 0 or n minus m, or when m is 0, then every tiling is made of a single piece. Either because the amplitude is non-negative Grassmannian itself, or it is empty. For k equal 1 and even m, it turns out that the cardinality is n minus 1 minus m choose 2 over m choose 2. No matter which tiling we will pick, it will always have this cardinality. All known cardinalities for m equal 2 were of the size n minus 2 choose k, while all the known tilings for m equal 4 were of size, well, this more complicated than Ariana number written in the table. It turns out that one can actually plug all these numbers into, well, one sequence. And that was first observed by Karp-Williams and Zhang. And that conjectured that for every even m, the amplituidron has a tiling of a cardinality, which is the McMahon number. Then Galashin and Lam conjectured an even stronger conjecture that all tilings of the amplituidron are of that size. So that's what we call the magic number conjecture, the conjecture that for even m, all tilings of all amplituidra are of the same size, and this size is this McMahon number. I should say that McMahon number appears in many contexts in combinatorics, representation theory, mathematical physics, in particular in Donaldson-Thomas invariance and quantum cohomology of Hilbert's scheme of points in the plane. And every time this number appears, it's in a cool theory. So I think that this is like one other justification for studying the amplituidron and for saying that the amplituidron is really a cool object. What we will show today, as I said, it's a joint work with Matteo, Melissa, and Lauren, is essentially the m equal 2 case of this conjecture, meaning that if we have a collection of cells that tile the amplituidron for m equal 2, then it is of the predicted cardinality. However, what we proved is not exactly this. We proved a slightly weaker claim. We proved that if there is a collection of cells such that for every positive v, it tiles the amplituidron, then it is of this cardinality. At the moment, I think that there are not known exotic tilings, the tilings that are tilings for only some v's and not for the others. And somehow the philosophy of amplituidron is that most properties are, well, not all of them, but many of the properties are actually v independent. So yeah, so I don't know if there are triangulations not in this size, but at least any tiling which is for every positive matrix v has this cardinality. And okay, in our papers we proved a bunch of other results. We proved something like this for the hypersimplex. We also studied a bit statistics of tilings, but I will not talk about these things here. Okay, so first of all, why should we even talk about m equal 2? Okay, so as a mathematician, well, I can talk about it because it's a nice object, but even I think that for physicists, there are a few reasons to be interested in it. First of all, it is simpler than m equal 4, but still it shares many of its features. Okay, so it allows us to study it or study some properties that we hope to find in the m equal 4 in the physical amplituidron, but in a simpler model. It has lots of mathematical structure. The m equal k equal 2 tree amplituidron is actually the one loop k equals 0 amplituidron. So it's another motivation. So I think that currently we have quite a few reasons to study it. So let's proceed. Yeah, there's a question. Okay. So I mean, I should say that already, whenever we have a map from a high dimensional space to a lower dimensional space, let's say a map from a high dimensional stratified space to a low dimensional space, it is very untypical that we can find strata of the domain that will tile the image. So that's already an untypical scenario. I mean, if we take a random function between spaces, we will not find it. But the spaces which have this magic number property, meaning that all their tilings are of the same size, are even more rare. So in order to get an intuition about okay, so what is the mechanism behind this property, let's test a few examples that, well, at least one of them we all know. The others, I guess some of you know, and we will see what we can take. Okay, so the simplest example of a space and all of those triangulations are of the same size is just a polygon. Whenever we have a polygon, an n-gon, then every triangulation of it has uses n-2 triangles. And okay, there are many proofs for this claim, but arguably the simplest one is the following. So the sum of angles of an n-gon is n-2 times pi. Now the sum of angles of each triangle is pi. And because if we have a triangulation without without adding internal points, then the angles are just summable, we see that in order to triangulate an n-gon, we need n-2 triangles. Okay, now let's proceed to polytopes. So polytopes in general may have no triangulation. And by the way, by triangulation in this context, I mean by simplices. It will not be the same type of tilings we will talk about later that will be in terms of positoid cells, but still like a very low order approximation. So polytopes in general may not have triangulation, and even if they do have, they need not to have the same cardinalities. However, there is an example of a very nice polytope. In a sense, it's the most convex polytope there is, which does have this property, and this is the cyclic polytope. So what's the cyclic polytope? So it's a polytope whose vertices are different points on the moment curve, or any other polytope that is combinatorially equivalent to such a polytope. And this space has many nice properties. For example, every subset of d over 2, at most d over 2, vertices is contained in a boundary facet or in a boundary face. So cyclic polytopes and their triangulations were studied by many authors. And about 30 years ago, Bayer proved that all triangulations of a d-dimensional cyclic polytope for even d have the same cardinality, which is n minus d over 2 minus 1, choose d over 2. And while we don't need it for the rest of the talk, I think that trying to understand why this property holds could give us a bit motivation to what we did in our work. So the most natural question is there an Engels argument for showing it, like we had for d equals 2? So the naive answer is that there cannot be, right? I mean, if I said before that polytopes in general don't have, so if there were an Engels argument, it should have worked for all polytopes. But actually, the non-naive answer is that is, and I'm going to show it. I think it's cute. I mean, we didn't plug it in the, we didn't put it in the paper for shortness. So if someone here is interested in this question in general, I suggest to stay tuned because I think it is cute, and I mean, I don't think it appears in literature. I mean, there are of course other proofs, but I think that this proof really explains why we have this phenomenon. Okay, so let's go back, I don't know, 67, 57. Okay, something which is 7 mod 10, it's between 60 and 57 years backwards to 67, where Perles and Shepard prove the following theorem. So let P be a simplicial polytope of dimension D. Okay, and let's denote by FIP the number of I faces of P, by phi IP the number of angles of its I faces, the sum of angles. Now, by angle, I mean the following thing. So if we have a vertex and we want to calculate the angle, we take a small sphere around where the vertex is the center, and we measure which portion of it is contained in the polytope. Okay, if we want to talk about the angle around an edge, again, we take a like sphere in the normal bundle, and again we calculate the portion which is contained inside the polytope. So there is a well-defined notion of an angle with respect to a vertex, edge, and so on. Okay, so also let's define f minus 1 of P and to be 1 and phi minus 1 of P to be 0. Okay, so this nice theorem, which, okay, so I'm not coming from combinatorics, but I don't think it is that well known, is an angular version or a geometric version of the Denham-Somerville equation. And it says that certain linear combinations of those angles with respect to faces give rise to face numbers. Okay, now interestingly, okay, so we have D linear relation, so maybe D plus 1. And it turns out that there exists linear combinations of them that allows us to use only angles of K faces for K smaller than D over 2. And the right-hand side will be linear combination of face numbers, again, for K smaller than D over 2. So I will not show it in general, I will just show you the D equal 4 case. So for D equal 4, we get the following equations. We get phi 0 minus phi 1 plus phi 2 minus phi 3 equals minus 1. Phi 0 minus 2 phi 1 plus 3 phi 2 minus 4 phi 3 equals minus f0. And minus phi 1 plus 3 phi 2 minus 6 phi 3 equals minus f1. And we can, so the linear, if we take the linear combination of them that gives on the left-hand side 3 phi 0 minus phi 1, we get on the right-hand side minus 6 plus 3f0 minus f1. Okay, now why is it interesting? So I remind you that the cyclic polytope has the property that any K face or K smaller than half dimension is actually a boundary face. Okay, which in analogy to what we had in the polygon, where we considered only angles at the vertices, angles at boundary faces are just summed if we have a triangulation. Okay, so let's see what it gives us. Okay, so we start with this equation. Now, if we apply it for the 4 simplex, we get that for simplex, 3 phi 0 minus phi 1 is minus 1. If we do it for the cyclic polytope on n vertices, well, so it has n vertices, so f0 is n. It has n choose 2 edges. So we get that 3 phi 0 of the cyclic polytope minus phi 1 of the cyclic polytope equals minus n minus 3 choose 2. Okay, and now we win, because as I said before, for every triangulation by simplices, we have that the sum of angles at vertices of the simplices equals the sum for the cyclic polytope. We have the same for the edges. Thus, oh no, do you see all my screen on the bottom row? Okay, I hope you do. So when we sum it, we get that minus n, which is the cardinality of the triangulation of the tiling, equals minus n minus 3 choose 2. Or in other words, the cardinality is of fixed side. Okay, so by the way, don't hesitate to stop me if you have any question at some point. Now let's try to see what we can take from this proof. Okay, so we can view the above proofs, both for the polygon and for the polytope, as follows. we first of all consider the chambers obtained by intersecting all the simplices or triangles or whatever we need for triangulations. And we associate a weight function to them, subject to the requirement that the sum of weights of chambers contained in a given simplex is constant. Okay, let me show why this is actually what we did before. So let's consider a pentagon. So before I said, okay, so we use the sum of angles of the vertices of the pentagon. So how can we relate them to the chambers? So the chambers are those bounded regions that you see that are intersections of all diagonals and so on. Well, one way is if we denote the three angles coming from A by A prime, A double prime, the ones from B by B prime, B double prime, and so on and so forth, then we can associate to the region in the middle, to the pentagon in the middle, the value 0. And for each other triangle touching a vertex or a triangle, just the sum of angles of the vertices, of the boundary vertices that touch it. Okay, so for example, for the triangles that touch A, we have B double prime plus A prime, and A double prime plus A. Okay, and now if we sum, so for me now these are the weights I assign to each chamber. Now, if I sum those weights over each simplex, which in this case is a polygon with vertices at the boundary, I get 1 pi, which is I just get the sum of angles of the polygon. And by the way, we can even make it less continuous. We can even make it discrete by making the following choice. So now some triangles get 2, other triangles get 1. And it's easy to see that every triangle whose vertices are at the boundary gets 5. Okay, so what I'm saying is that, well, essentially what we did in the previous examples was really followed this strategy. Understanding the chambers, assigning some weight function to them, and verifying or choosing the weight function in a way that the sum over all, over chambers in a given simplex or piece are the same. Okay, so now
There is a question.
Yeah.
Is the existence of this weight function obvious since you have a requirement for the type?
Could you repeat the question? I'm sorry.
Sorry, is the existence of this weight function obvious?
Obvious. I mean, for which spaces? I mean, whenever you have this property, whenever you can apply this strategy in particular, you are in the situation that all your tilings will have the same cardinality. Most spaces don't have it. So if you ask if it and if and only an if and only if question, I'm not sure, but maybe it's not unlikely that yes. I mean, it's not unlikely that yes. I mean, in the end, it might be just a linear algebra question. We don't have too many examples of these spaces. I mean, okay, there are a few more polytopes that satisfy this property. I mean, if you're interested, you can look in the original paper by Bayer. Maybe since then there were also other polytopes were found, but I don't think that for, let's say, curvy spaces, of algebraic geometric origin, this property, have been observed before. So it's a bit hard to say. But for the amplitude, for the m equal 2 amplitude, we are going to follow this strategy, but in a non-trivial way. Are there further questions? Okay, so let's move on to the amplitude. Okay, so we would like to follow a similar strategy. In order to do it, we will first of all classify the so-called W chambers. What are W chambers? These are the chambers that are obtained by intersecting all m equal to tiles. So in the previous examples, we were interested in triangulation by simplified. In this case, we're interested in triangulation using tiles. So it makes sense that we will be interested in the chambers obtained by intersecting those tiles. Then we will associate a weight function for each W chamber. And we will show that the sum of weights of W chambers contained in a tile is a constant. And then just by the previous, well, what we saw in the previous cases, we will see that all tilings have the same cardinality, which is just the total sum of all W chambers weights over this constant. Okay, so that's what we are going to do right now. And well, it will be nice that actually also the weights themselves will be very nice objects, but I don't want to make spoilers. Okay, so as I remind you, in the statement of our theorem, we talked about tilings for all Z. So in order to somehow be able to handle this type of tiling in the most natural way, let me move slightly from the usual amplitude to the positive section of the universal amplitude. By the way, it's not exactly what we did in the paper. I mean, it is completely equivalent to what we did in the paper, but in the paper we use different terminology, and so it's not that you're going to find exactly these notations or these spaces in the paper, but yeah, essentially it's the same proof. So consider the positive section of the universal amplitude. By that I mean, instead of looking only at the image of the amplitude map for a given Z, we consider pairs which are of the form Y and Z, where Y is an amplitude point and Z is a positive matrix. Okay, so this space, well, it comes with a map from the non-negative Grassmannian times the positive matrices into it. We just take C, which is a non-negative matrix, and Z, which is a positive matrix, and outputs C, V transpose, and Z. Now, a positoid cell gives rise to a tile for each positive Z, even only if the map, this map R, from the positoid times the positive matrices is injective. Okay, so before when I mentioned tiles, I only required that the map from a positoid cell will be injective because I fixed the matrix. But now I let the matrix, the positive matrix, vary. So I will say that something is a tile if the same map from the product positoid times positive matrices is injective. Okay, and we will call it an all-V tile. You can ignore the open. Open is just for consistency with the paper. A collection of positoid cells gives rise to a tiling for all positive Z, if and only if each positoid there is an all-Z tile. Gives rise to a tile for all positive Z, and the images of S times, those positoids times the positive matrices tile this total amplitude. Okay, so I just moved from a single object to a family. The most standard step people do in geometry. Okay, and I will also need another ingredient, which is the momentum twistor coordinates. I will call them just twistors for shortness. Which given a point in the total amplitude on YZ, and M indices returns the determinant of the matrix obtained by appending to Y the rows VI1 transpose to VIM transpose. Okay, so it becomes a square matrix and we can take its determinant. So it's essentially the usual momentum twistor that we always talk about, but okay, for general M, and we let these out, but it's exactly the same. Okay, so in their beautiful paper from 3 or 4 years ago, Matteo, Melissa, and Lauren classified all M equal to tiles. They showed that these tiles are in bijection with the so-called bicolored subdivision of type Kn. So a bicolored subdivision is just like in this picture. It's a collection of black polygons inside an n-gon. They are non-intersecting. Okay, so when we and the number, so the number n is just the number of vertices of the n-gon. In this case, it is 9. And the number 5 is the area. By area, I mean that if we triangulate the black polygons, how many triangles do we have to use? So in this case, it is 5, 9. And what they showed was that, in fact, the tile is the semi-algebraic set defined by fixing the signs of certain twistor coordinates, which are dictated by the combinatorics of the subdivision. So, okay, so if sigma is a bicolor subdivision, then the corresponding tile T sigma, and okay, as I said, I only talk about all V, but it's essentially the same. So the bicolor subdivision, sorry, the tile TV is just the collection of all points YV in the Grassmannian times positive matrices, which satisfy that the twistor IJ has a given sign for every compatible arc IJ. So, okay, so I need to tell you here two things. What are compatible arcs and what is the area? Let's see if I can annotate it and it will make it. Okay, so an arc is compatible if the straight line that realizes this arc doesn't cross from the interior of a black polygon to the interior of a white polygon. Okay, so for example,
Excuse me, Ran, wait a second, the screen is black.
okay, so I was in the course of explaining what are bicolor subdivision, or sorry, how do they encode the tile. So given the combinatorial data of a bicolor subdivision, the tile is the collection of amplituidron points such that some of their twistor coordinates have a given sign. Okay, so which twistor coordinates? So twistor coordinates for compatible arcs. A compatible arc is an arc that doesn't cross from a black area to a white area. For example, 3, 7 is a compatible arc, but 1, 5 is not. Okay? Now, for any compatible arc, we can talk about the area to the left of it. How many triangles do we have to the left of it? And what Matteo, Melissa, and Lauren showed is that a point is in the tile if and only if for every compatible arc, the sign of its twistor coordinate, ij, where ij is the arc, is exactly -1 to the area, -1 to the number of black triangles we see from the left of it. Okay, so it is a very nice example that the combinatoric somehow talks with the geometry. Okay, and they also defined W chambers. So the W chambers, so we can ask, what about a subset of this total amplituidron that have a fixed sign with respect to every twistor, not only compatible arcs, every twistor, every entries to twistor. So they defined W chamber to be such a subset, that which is defined by fixing and choose two signs and looking which points the twistor coordinate have this sign. And of course, it's not that we have 2 to the power of n choose 2 chambers, because there are many constraints. For example, we know that the twistors I+1 are always positive. Also, we know that certain sequences of twistors have a given sign flip. So we see that not all possible chambers are non-empty. And what Matteo, Melissa, and Lauren did, they classified the non-empty ones. And they showed that they are indexed by a certain collection of permutations. So, okay, so I think that because of time considerations, I will not describe exactly what these permutations are or how what is the relation between the permutation and the sign of a twistor. But let's remember that every chamber, every W chamber, is indexed by a given permutation from a set that we denote by dk plus 1. Okay, so now let's move to define the weights. It turns out that the weight that does the work is actually a very familiar function from physics, from this world of amplitude, and it is the Park-Taylor function. Okay, so what's the Park-Taylor function of permutation? So it is 1 over the Fluker W1, W2, W2, W3, and so on. So we think about it as an element in the ring of functions over the affine point of the Grassmannian 2M. Okay, so for example, if our permutation is 2, 1, 4, 3, then the Park-Taylor function will be 1 over P21 times P14 times P43 times P32, and we can reorder it by playing with some signs to a nicer order. And okay, perhaps some of you actually know better the form of this function after gauge fixing. So it turns out that we can also define the Park-Taylor function for the Grassmannian mod torus. And if we consider any points with no in the positive Grassmannian mod torus has in its orbit a point whose top row is just 1, and the bottom rows are arbitrary Z1 to Zn. And under this gauge fixing, the Park-Taylor just becomes the familiar expression 1 over ZW2 minus W1, ZW3 minus ZW2, and so on. Okay, so currently what we have, so we have our chambers, which are the W chambers from before, the ones that were indexed by permutations. And we have our weight functions. So the magic number property will now follow from the following proposition. So for every tile T of sigma, the sum of Park-Taylor's weights of its W chambers, sorry, I wrote here Park-Taylor of delta W, but I meant Park-Taylor of W. So the sum of the Park-Taylor of its W chambers equals a constant, which in this case is minus 1 to the k times the Park-Taylor of the identity. Okay, so why does it imply the claim? So this is essentially equivalent to what we saw before, but let me do it again. So suppose we have an Olvi tiling T. So, and if we sum all the expressions for the tiles, on the one hand, we get T, the cardinality of T times this constant, minus 1 to the k pt of the identity. On the other hand, what we get is just the sum of all Park-Taylors over all possible W chambers, which implies that the cardinality is just the sum of all Park-Taylors that correspond to W chambers over a constant, pt of the identity. Okay, so in the remaining time we have, I will, if there are no questions, I will quickly have a short overview of the proof. Okay, so the first step is to characterize which W chambers are contained in a given tile. And what we showed is that, again, this can be very nicely read from the combinatorics, from the bicolored subdivision. So if sigma is a bicolored subdivision, then we can write the tile as the union. Okay, actually, I should have been slightly more careful. I should have taken the closure. So it's the closure of union of the W chambers for a W, which we will think of as an order, which satisfy the following two requirements. For every white polygon with vertices V1 to VR, we expect to, when we restrict the order to V1 to VR, we expect them to see in that order. For every black polygon with vertices V1 to VR in counterclockwise order, this is the order that we see V1 to VR in W. Okay, let me give an example. So in this example, we have a bicolored subdivision for n equals 6 and k equal 2. And the requirement is that we see that if we restrict W to 1, 2, and 3, we see them in a clockwise order. And the same if we restrict it to 1, 4, and 6, because these are white triangles. On the other hand, if we look at the black triangle, it puts the constraints that we see 1, 4, 3, and 4, 6, 5 in that order. Okay, so here's the list of permutations. Okay, so one example is that 5, 1, 2, 4, 3, 6. So we can see that if we restrict it to 1, 2, and 3, it is really in that order. If we restrict it to 1, 4, and 6, it's in the expected order, and so on. Okay, so this gives us a characterization of the W chambers contained in a given tile. Okay, now we want to prove, I mean, the proposition is to prove that the sum of Park-Taylor functions over W chambers in a tile equals -1 to the k times PT of the identity. Okay, so if we look at the gauge fix, it is equivalent to saying that the sum of the gauge fixed Park-Taylor expressions over W chambers in the tile minus -1 to the k over the Park-Taylor identity equals 0. Okay, now the left-hand side is a rational function of weight -n. All its poles are simple and lie on the fat diagonal, meaning Vi equals Vj for some I and j. And what we are going to show is that there are no poles at Vi minus Vj if the arc Ij is not a boundary of a black or a white polygon. And there are no poles at the boundary arcs. So this means that all possible poles can only be for internal boundaries of polygons. But there are at most n-3 in such internal boundaries, but we need at least n poles in order to be in weight -n. So it means that the left-hand side is 0. Okay? So in the next 2 slides, I will explain how we do this. So how do we rule out that an arc which is not a boundary of a polygon is that there is a pole there? So we'll use an involution argument. So a pole Vi minus Vj can appear in a permutation W only if for some h, Wh is I and Wh plus 1 is j, or the opposite. Okay, so let W be such permutation, let W prime be the opposite, the one in which we switch between Wh and Wh plus 1. Now, by the characterization above of W chambers in a tile, we see that if the arc Ij is not a boundary of a polygon in sigma, then if W belongs to T sigma, then also the W prime simplex will belong to T, will be contained in T sigma. And now an easy calculation just shows that when we sum the two, we lose the pole at Vi minus Vj. Okay, so this shows that all possible poles are at boundaries of polygons. It doesn't exclude yet external boundaries. So let's exclude this. So this is actually an inductive argument. So the residue at Vi minus Vi plus 1 is, and I say residue in quotation marks because it's not a form, it's a function, so we need to be a bit careful. But if we take the equation that we are interested in, that we want to prove here, and we consider the residue at vi minus vi plus 1, what we will get is essentially the n minus 1 problem of proving what we will get is essentially the same identity, but for the bipolar subdivision obtained by shrinking the boundary arc I plus 1, by identifying the I and I plus 1. Okay, so if by induction it were 0, then we see that the residue at this possible divisor will also be 0. Okay, so with that, we're done. And so thank you very much.